In this video, we're going to talk about motion in space. So let's suppose that we have a particle that has a position at time t given by a vector function r of t. We're going to define velocity of the particle that moves along this vector function, much like what we did for velocity of a particle that moves along a line. So the way we did that, of course, back in Calc 1 was to take the derivative, and said that if we take the derivative of a position function, we get the velocity of that particular object. So the exact same thing here is going to be true. We're going to take the derivative of the vector valued function that's giving the position of the particle at time t, and we'll call that the velocity vector of that particular particle. If we want to know how fast the particle is moving at that particular moment, we would take the magnitude of the velocity vector, which would be the magnitude, of course, of the derivative, which is just then, remembering what we did with arc length, this would be the derivative of arc length with respect to time, which makes sense for what we would mean by speed. How fast is the object moving? And of course, it's moving along a curved path with respect to time elapsing. All right, so let's do an example. Let's say we have the position of a particle be given to us by this two-dimensional vector function 4 cosine t times I plus 4 sine t times j. And we want to find the velocity and the acceleration vectors at time t. Well, we're going to find the first derivative to give us the velocity. So we'll get negative 4 sine of ti plus 4 cosine tj. Acceleration is defined the same way it was back in Calc 1. It'll be the second derivative of our vector function. So in this case, we'll have negative 4 cosine ti minus 4 sine tj. So if we say we wanted the velocity at time pi over 3, we would plug pi over 3 in for t, and we would get negative 2 root 3i plus 2j for the velocity, and negative 2i minus 2 root 3j for the acceleration. So let's illustrate this on a graph. If we recognize the form of this vector function as 4 cosine t and 4 sine t for your x and y coordinates, that's a particle that's moving in a circular motion, and it would be going counterclockwise as t increases in that case. So your vector at pi over 3, your velocity vector, is going to be tangent to that circle, and we see that in this case. The acceleration vector is pointing inward into the circle, which makes sense, right? Because our object is getting pulled in a circular motion sense, if you will. And so its velocity is going to have to change, being pulled inward toward the center of the circle. Let's do another example. Let's say we have a projectile being fired upward from a height of r0 and a speed of v0. Now the speed, of course, we don't know what direction that speed's in, so we need an angle, theta, with respect to the ground. If we're doing projectile motion, if we ignore air resistance, then gravity is the only force acting on that object. Let's see if we can determine what the position vector is at time t. Well, if gravity is the only force acting on the object, and again, we're going to think about this in 2 dimensions. If gravity is the only object, then gravity pulls the object downward towards ground level. So our acceleration function is negative what the force, the acceleration due to gravity here, the g function, or excuse me, the g constant times j will be our acceleration vector. Let's work backward to get to our position function. Before we get to the position function, we need to get to the velocity function. So we'll take an antiderivative of our acceleration. That's an easy antiderivative to take. That would just be negative gt times j. We have some constant vector, since we're doing an indefinite integral here. However, we're told that the initial speed is v0 and the initial angle is is theta. So we should be able to figure out what the velocity vector is at time 0. And we can do that just with a little bit of right triangle trigonometry, right? We have the speed going at v0 with an angle of theta, so v0 cosine theta will give you the x coordinate of the velocity, and the v0 sine theta will give you the y coordinate, if you will, of the velocity, which way the velocity is pointing. And that turns out to be your arbitrary constant vector, because we plug in 0 for t here, this term goes away. So now we're ready to work backward to get our position function. So we do our integral of the velocity after plugging in our constant. Take an antiderivative. We'll get a v naught cosine t. There aren't any t, v naught cosine theta. There are no t's here, so when I do the antiderivative, you get a v naught cosine theta times t times I. Likewise, we get a v naught sine theta times t here. Now we're integrating t, we get a 1/2 t squared for the j component as well. And we have another arbitrary constant. We're told that the object is fired upward from a height of r naught. Fired upward from a height of r naught. Well, the r naught's talking about distance above ground level. We haven't moved left or right at all. So the r naught vector is just r naught j, which will be our arbitrary constant again in this case. So now we have what our position looks like for as far as a position function. We've got v naught cosine t times I. There is nothing acting in the x direction. So the position at time t in the x direction is just rate times time. Distance equals rate times time formula that you learned a long time ago. It's just that the rate has that cosine theta in it because we have to know how much rate is going in the x direction versus how much rate is going in the y direction. The j component's a little bit more complicated, but you've probably seen this formula before if you've done some projectile motion stuff. Here's your initial height. This is your initial velocity. In this case, it's the initial velocity in the y direction times t, and then 1/2 times the acceleration due to gravity constant here times your t squared. So these formulas should look familiar to you, maybe written in a slightly different form, but the first one is just distance equals rate times time, and the second one is your projectile motion formula in a vertical from a particle that's been fired vertically. All right, let's switch gears a little bit and let's talk about the tangential and normal components of acceleration. If we have a position vector at time t, we know how to compute the unit tangent vector. Now we're calling r prime v, so that's just substituting v for r prime. We can rearrange this particular equation. Have our velocity vector function is the speed, so we're letting little v without the magnitude be the magnitude of v. That's the speed times the tangent vector. Our acceleration, of course, is the derivative of velocity. We can differentiate that using product rule because we have this expression now for the velocity vector. So this is just the product rule being applied to the v times t, the non-vector v times t. We know that the unit normal vector is defined to be the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. So all we're doing is making that substitution here. We still have a v prime here in front of the t. Here is just substituting in for curvature. So remember that your curvature is defined, one of the ways we can compute curvature is that we can take the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative. Well, the magnitude of the derivative in this case is the magnitude of the velocity vector, which we're denoting with a little v. So we need to adjust with a v squared here to make sure that we have the right thing in the denominator for curvature. All right, so we've got curvature times v squared times n for this piece. All right, so we've now written, the whole point of going through all of this is that we've now written the acceleration vector as a scalar function times the unit tangent vector plus another scalar function times the unit normal vector. So we've broken this up into two pieces. So we call the first piece the tangential component of acceleration and the second piece the normal component of acceleration, these two scalar functions that we just figured out. So if we have a picture of what's going on, here is our unit tangent vector going this way. Here is our unit normal vector going this way. The long vector here is your acceleration vector. The distance from along we should say the projection. The distance that's along the unit tangent vector, where we do this projection down of our acceleration down onto the unit tangent vector, that's our tangential component of acceleration. If we go the other way and project basically perpendicularly to that tangent vector, or project onto the unit normal vector, if you think about this line being translated over here, that distance is your normal component of the acceleration. So this is how much acceleration is going in the normal direction. This is how much acceleration is going in the tangent direction. Well, much like what we did with curvature formulas, it's handy to have our tangential and normal components of acceleration being written in terms of r of t and its derivatives. Dot product here for v and a, just using our formulas that we came up with. When we do the dot product, we'll get v times v prime times the dot product of t with itself, plus the curvature times the velocity squared, or excuse me, the speed squared, times the dot product of the tangent and the normal vector. Unit tangent vector has magnitude 1, so t dot t is 1. Tangent and normal vector are orthogonal to each other, so that's 0. So we just get v times v prime. We know that their tangential component of acceleration is just v prime, so we can solve for v prime, and we get v dot a over v for the tangential component of acceleration, which we can write in terms of r and its derivatives as r prime dot r double prime over the magnitude of r prime. For the normal component, we know it's curvature times v squared. Well, curvature, here's our formula in terms of r, right? It's r prime cross r double prime over magnitude of r prime cubed. V was magnitude of r prime, so this is just magnitude of r prime squared. And then simplifying, we get r prime cross r double prime over r prime, and magnitude of those things. So we get magnitude of r prime cross r double prime over magnitude of r prime.